Alright, this is the second video of the first week, and from this video, I'm gonna use the new lecture slide posted on the course website. So my aim is to cover three remaining topics in chapter 5, meaning that I have to take three more videos, and plus, unfortunately, I spent a little bit more time in the first video, so I have to go a little bit fast. So we have a equivalence between these two conditions, non-singularity and non-zero determinant. And in this video, we're going to set one more equivalence between invertibility and the previous two conditions. And remember, whenever A is invertible, so inverse matrix exists, and we know it is uniquely determined. So, system of linear equation Ax equals B has a unique solution, x star, can be found by pre-multiplying A inverse to this system of linear equations. So we now finally study how to find inverse matrix, and that's the core of linear algebra. All right, but in order to find the inverse matrix, we have to study one more property of determinant. That is the next theorem. All right, and in order to explain this, let me consider first 3 by 3 matrix. And remember, if we have a 3 by 3 matrix A, its determinant is, if we do Laplace expansion by the ith row of this matrix, then it's going to be A sub I1, C sub I1, I2, C sub I2, and I3, C sub I3. Okay? And we can re-express this linear combination as the dot product between two vectors. And look at this linear combination. The first entry is nothing but the ith row vector of matrix A. So A sub I, that is A sub I1, I2, I3. And another vector, cofactors, C sub I1, I2, I3. So define C sub I as the list of these three cofactors. And this linear combination is nothing but dot product between these two. Okay, so with this in mind, now let me read the statement. So we have n by n matrix A and define C sub j as the n tuple vector whose kth coordinate is the cofactor obtained by deleting row j. J is the subscript of C sub j, and the column k of matrix A. All right, so the first coordinate of this vector, C sub j, is a cofactor C sub j1, so obtained by deleting row j and the first column. And the second coordinate, j2, deleting row j and the second column, and so on. Okay, so just like this C sub I, so in 3 by 3 case, we have three elements, okay, three cofactors. Okay, and in case of n by n, we can generate this C sub j as a n tuple vector. And the theorem states that the dot product between the ith row of matrix A and these cofactors, C sub j, is going to be 0 whenever these two subscripts I and j are different. And when they are equal to each other, we have a determinant of matrix A. Okay? And we already know this fact by the definition of the determinant, because a determinant of a matrix A is a dot product between a one row vector of matrix A and its corresponding cofactor. Okay? But the theorem states that, surprisingly, when these two subscripts differ, then the dot product gives us value 0. All right. So whenever two subscripts are different, we call that cofactors. C sub j are the alien cofactors. Okay. So the theorem simply states that dot product with alien cofactors is going to be 0. All right, and before proving this theorem, let me show you one example. So here we are given by 3 by 3 matrix. And think about the C sub 2. Okay, so the list of cofactors generated by the second row. So C sub 2 1, 2 2, 2 3. Okay, so for all these entries, we have to eliminate the second row. And the first entry, C sub 2 1, is going to be negative 1 to the power 2 plus 1. And the determinant, so we are left with this 2 by 2, 1 and 2, 0, 3, right? After eliminating the first column. So that is negative 3. C sub 2, 2, negative 1 to the power 4. So after eliminating the second column, then we have 4, 2, 1, 3. So which is 10, right? And I already computed it, the last one, C sub 2, 3, turns out to be 1. So these cofactors are just the three numbers which are negative 3, 10, and 1 respectively. All right. Now let me compute the dot product with these alien cofactors. So A sub 1, the first row vector of matrix A, and this alien cofactor. So 4, 1, 2, dot, negative 3, 10, 1. All right. So negative 12 plus 10 plus 2. That is indeed 0. Okay. You can self-verify that the dot product between A sub 3, so the third row vector of matrix A, 1, 0, 3, and this cofactors, this vector, is going to be 0 as well. All right, so the previous theorem is indeed true. And now let me illustrate the key idea behind this theorem. All right, and the idea can be developed from an analysis of the 3 by 3 case. So we don't have to go to an n by n case to figure out the key idea. So here we are given by 3 by 3 matrix A. Now let's compare this with a matrix A star. Okay, and I constructed this A star just replacing the second row of matrix A with the first one. Okay, so as a result, the first row vector and second row vector are the same. All right, and if we compare these two, then we can observe that these two matrices give rise to the same cofactors C sub 2. Because in order to make a C sub 2 from matrix A, we have to eliminate the second row. All right, so C sub 2, the three cofactors, will be made of these 6 remaining entries, the first row and the third row. Now think about, so think that we generate the C sub 2 from this matrix A star, right? And just like this, we eliminate the second row, and the remaining entries are the same as before, all right? So the cofactors C sub 2 from this matrix A star is the same as the cofactor from A, matrix A. In other words, these two matrices give us to the same cofactors C sub 2. By the way, the second matrix has a determinant of 0. Why? Because the two row vectors are the same. And remember, by the last property of the determinant, row addition does have no impact on the determinant. So let me do one row addition here. So multiply the first row by negative 1 and add it to the second. Then we can make the second row vector be 0, 0, 0, 0. And the third row vector So the matrix determinant of a matrix A star is the same as the determinant of this, but it has a 1, 0 row vector, and by the second property of the determinant, so we know this matrix has determinant 0. Okay, so A star has a determinant of 0. All right, then let me do Laplace expansion by the second row of A star. Okay, so by definition, it's going to be the dot product between A sub 2 star and C sub 2, because this A star gives us the same expression about these cofactors. And the second row of A star is the same as the first row vector of matrix A, right? So A2 star is a same as A sub 1 star of A sub 1. Okay. So this is the determinant. So we know the dot product value is 0. So the dot product between this A sub 1 and alien cofactor is equal to 0 as well. All right. So that is the basic idea of the theorem 5.1. So the dot product with a alien cofactor is going to be 0. All right. And the previous theorem can be used to establish the last property of determinant, that is, row addition has no impact on the determinant. Okay, so in the previous video, I just introduced that property, and here now I'm going to prove this. All right. So matrix R is a row echelon from matrix A obtained only by row addition, and the two matrices have the same determinant. Why? So here we have matrix A, say 3 by 3. Okay, and I can rewrite this A sub 1, A sub 2, A sub 3. Okay, because each entry now is a row vector. Okay, so we can just vertically stack the each row vector for the original matrix 3 by 3. All right, and let me do just one row addition here. So multiply the first row vector by k and add it to the second to make this matrix A1, A sub 2 plus k times A1 and A3. Okay, and think about the determinant of this new matrix. All right, and let me do the Laplace expansion by the second row. All right, that is going to be A sub 2 plus k A sub 1 dot C sub 2, right? And because we can distribute this dot product, so this expression is the same as A2 dot C sub 2 plus k A1 dot C sub 2. All right, but the A2 dot C sub 2 is the determinant of matrix A. That is just the Laplace expansion by the second row of matrix A. So we have determinant of A, and this is 0 by the previous theorem because it's the dot product with a alien cofactor. So determinant of this is the same as determinant of the original matrix. Okay? In other words, row addition itself, that alone, has no impact on the determinant. All right. Now we are ready to find the inverse matrix. So using the previous theorem, dot product with the alien cofactor is always equal to 0. We are going to find the algorithm of computing the inverse matrix. Okay. So to build an idea, we start with a 2 by 2. So then whose determinant is non-zero? Okay, this is very important. Okay, so we start from a non-singular matrix. So now define inverse matrix as X. So X is an A inverse. And it's defined as a 2 by 2 matrix satisfying the product between A and X. is going to be identity matrix. Right? So 1, 0 and 0, 1. Right? And now we're going to split this equation number 1 into two pieces. So by decomposing column by column, so matrix A times the first column of matrix X is going to be 1, 0, right? And the second piece is matrix A times the second column of matrix X is going to be 0, 1. Okay, so A11, A12, 21, 22, and the second column of matrix X is going to be 0, 1. Okay. In terms of matrices, so this is A times the first column of matrix X is going to be E super 1. So the first unit vector in two-dimensional space. And the second equation tells us A times the second column of matrix X is going to be E super 2. So the second unit vector in two-dimensional space, 0, 1. All right? And then by the definition of multiplication, A times X super 1 is going to be 2 by 1 matrix. And the first entry is A sub 1 dot X super 1. Because multiplication is determined by one row vector of the first matrix and the column vector of the second matrix. And the second entry can be written as A sub 2 dot X super 2. Or X super 1. Right? Because we multiply by the first column of matrix X. And can rewrite this as well. So this is A sub 1 dot X super 2 and A sub 2 dot X super 2. Right? And that is equal to second unit vector 0, 1. And this is equal to 1, 0. All right? And now look at the equation. A sub 1 dot x1 is equal to 1. A sub 2 dot x super 2 also 1. And whenever scripts are different, it's going to be 0. Right? So finding inverse matrix is equivalent to solving this one pair of linear equations, right? And it has one salient feature, that is, whenever two scripts are equal to each other, the dot product should be equal to 1. And whenever they differ, dot product is equal to 0. So we have to find this x, each column of matrix X, satisfying these equations. But remember that from the previous theorem, we know the dot product between each row vector and its cofactors gives us the determinant. So A sub 1 dot C sub 1 and A sub 2 dot C sub 2 are equal to determinant of matrix A. So they give us the same value. And the dot product between row vector and its alien cofactors, so A sub 1 dot C sub 2, whenever the two scripts are different, we have a value 0. Okay, so if we set x super 1 equal to 1 over determinant A bar and C sub 1, and set x2 be equal to 1 over determinant C sub 2. All right, then A sub 1 dot x super 1, that is going to be 0, or that is going to be 1, because A sub 1 dot C sub 1 gives us determinant, and we have a reciprocal here, So they will be cancelled. So it's going to be 1. But a sub 2 dot x super 1, now it involves a dot product with an alien cofactor. So it's going to be 0. Okay, and a sub 2, so a sub 1 dot x super 2. Now it involves a dot product with the alien cofactor. So x super 2 has a c sub 2, and we compute the dot product between dot product with a sub 1. So it's going to be 0. And finally, a sub 2 dot x super 2, that is 1. All right. So these two are indeed the solution to the previous linear system or system of linear equations. All right. So the matrix X, the inverse matrix of A, it has 2 columns, x super 1, x super 2. And x super 1 turns out to be the cofactors, c sub 1, and multiplied by 1 over the determinant. And x super 2 is going to be 1 over the determinant times the cofactor c sub 2. Okay, and each cofactors are the 2-dimensional vectors. So c sub 1 has a c sub 1 1 and c sub 1 2, and c sub 2 2 1 and 2 2. So these 2 by 2 matrix is going to be the inverse matrix of matrix A. All right, so in case of, so when A is given by A, B, C, D is 2 by 2, then we know the determinant is AD minus BC. Okay. Now this 2 by 2 matrix is going to be C sub 1 1 is D, and 2 1 becomes minus B, and C sub 1 2 becomes negative C, and 2 2 becomes A. All right. So we interchange the diagonal entries D and A, okay, and put negative signs on off diagonals. So negative B becomes negative B, C becomes negative C. That is a formula, simple formula for the inverse matrix of 2 by 2. Okay. Also tells us the basic idea about how to compute the inverse matrix. Okay. Each column of inverse matrix is going to be 1 over determinant of the cofactors. All right. So we can extend this idea to 3 by 3. So find the inverse matrix in case of a 3 by 3 is equivalent to finding a solution to the, now we have 3 linear equations. So system of 3 linear equations. All right. And the solution to this system, because this system has the same feature as this. Whenever scripts are identical, dot product is equal to 1. When they differ, and dot product should be equal to 0. Okay, so the solution to this equation is going to be 1 over determinant. X super 1 is going to be c sub 1, x super 2, c sub 2, and so on. Okay, and in case of a 3 by 3, c sub 1 is going to be a 3-tuple vector. So from c sub 1 1 to c sub 1 3, and c sub 2 from 2 1 to 2 3, and c sub 3 from 3 1 to 3 3. Okay, so if we define cofactor matrix, C as C sub 1 1, 1 2, 1 3, and 2 1, 2 2, 2 2, 2 3, and 3 1, 3 2, 3 3, because the first subscript usually stands for row, and second stands for the column. Okay, so this is the right way to write a matrix. This is the right way to write a matrix. But this matrix C is just the transpose of this cofactor matrix. And we call this adjoint of matrix A. Okay, and written by ADJ. So the first three letters of this and the matrix A. Okay, so the inverse matrix of 3 by 3 in 3 by 3 case is a 1 over the determinant times adjoint matrix of matrix A. All right, and before doing this example, it can be extended to n by n. So let me tell you, the same algorithm is readily applicable to n by n matrix. So regardless of the dimension, finding inverse matrix is equivalent to finding the system of linear equations that has the feature I told you. So A inverse is going to be 1 over determinant, adjoint of matrix A. And remember, adjoint of matrix A is a transpose of the cofactor matrix. Okay, so the first row vector of C becomes a first column vector, and the second row vector becomes the second column, and so on. All right. So the ijth entry of the inverse matrix is going to be 1 over determinant, 1 over determinant A times the ij entry of the adjoint of matrix A. Okay, which is, because adjoint is a cis transpose, so 1 over determinant C sub ji. Okay, so this is a general formula for matrix inversion. How to compute inverse matrix in case of n by n. Okay, and let me summarize our discussion using this example. So find the inverse matrix of this 3 by 3 matrix. All right, and let me first compute the determinant of this matrix A. Okay, by the way, I highlighted the non-singularity. So non-zero matrix A is important in finding inverse matrix, because if matrix A has a zero determinant, then this guy is not defined. We can set x super 1 be equal to 1 over determinant, right? That becomes 1 over 0. It's an undefined number. So this kind of job can be done, right? So this is very important. Non-zero determinant is very important in finding inverse matrix. All right. So with that in mind, let me first compute the determinant of this matrix. Okay, and let me use the second column, 1, 3, 0, because it has a number 1 and number 0. Okay, so the determinant of A is going to be 1 times C sub 2, 1, 3 times C sub 2, 2, and 0 times C sub 2, 3. Sorry, it's I was wrong with the subscripts. So C sub 1, 2, 2, 2, and 3, 2, because I used the second column. Okay, so the second subscript should be equal to 2. And C sub 1, 2 is going to be negative 1 to the power 3. So 0, 2, 3, 7, which is a 6. And C sub 2, 2. C sub 2, 2 is 4, negative 1, 3, 7. So 31, I guess. And C sub 3, 2. Because we don't have to compute this for the determinant, but in the end, we needed this information, right? Because we have to compute the adjoint of matrix A. So the transpose of cofactor matrix. So in order to find the inverse matrix, we have to find all cofactors, Right? So C sub 3, 2. Now eliminating the third row and the second column. And we have a negative sign in front because the sum of the subscripts are, sum of the subscripts is a odd number. So 4, negative 1, and 0, 2. So that is negative 8. Okay. And I already computed other cofactors. Oh, so by the way, the determinant of matrix A is therefore, so 6 plus 3 times 31, so 99, I guess. 99, I guess. 93 plus 6, yeah, 99. All right, so matrix A has a determinant of 99. That is a non-zero number. Okay, so now let me compute the cofactor matrix C. Okay, and C sub 1, 1 is 21. 1, 2. 1, 2 is right here, 6. And 1, 3 is negative 9. And 2, 1 is negative 7. 2, 2 is right here, 31. And 2, 3 is a 3. And 3, 1 is 5. 3, 2, negative 8. And 3, 3 is 12. Okay. So by eliminating each column and each row, I think you're able to compute these cofactor matrices. All right. Then adjoint A is transpose of this. So 21, negative 7, 5, 6, 31, negative 8, negative 9, 3, 12. So as a result, A inverse is going to be 1 over 99, the reciprocal of the determinant, and multiplied by this adjoint of matrix A. All right. So this is the way of finding inverse matrix. As you can easily imagine that it entails a heavy computation. But once again, the main objective is not, compute a inverse matrix of a, general n by n. The main objective is to understand the algorithm. All right. And in this video, I explained the algorithm of computing inverse matrix. And the basic idea comes from the one property of determinant, that is a theorem 5.1. And the finding inverse matrix is the same as, is equivalent to solving linear equations, where it is. Finding inverse matrix is equivalent to solving a pair of equations having this feature. So the previous theorem helps us to identify solutions, all right? And turns out that inverse matrix is going to be transpose of cofactors and multiplied by reciprocal of the determinant. All right? Hope you guys enjoyed this video and see you guys in the next.